lecture we continue our discussion on sequencing and scheduling. In the previous lecture we had seen the assumptions, the objectives and different types of sequencing and scheduling problems. We will now address each one of the problems in detail and see how we can optimize or minimize the chosen objective. So, the first problem that we will be looking at is a single machine sequencing problem. We take a numerical example to explain a few ideas in single machine sequencing. So, we consider situation with 4 jobs which we call J1, J2, J3 and J4. So, let the processing times be 6, 10, 8 and 6 units of time. These units of time can be minutes, can be hours and so on. So, it is customary to keep them as minutes. Now, we want to try and sequence them, send them on a single machine. Now, the single machine is here and we want to send them for processing on the single machine, so that we try and optimize or minimize a chosen objective. Now, there are 4 jobs J1, J2, J3 and J4, and these 4 jobs can be arranged in 4 factorial ways. In general, if we have n jobs, they can be arranged in n factorial ways. Now, depending on the objective, one or more of these n factorial sequences will turn out to be optimum. Now, let us look at minimizing make span. Now, first let us explain the computation of completion times and then we try and look at each of the objectives. Now, if this is a machine and we try and send them in the given order, say J1, J2, J3 and J4. Now, J1 enters at time equal to 0. So, the completion time for J1, J2, J3 and J4, J1 will enter at time equal to 0 and come out at time equal to 6. So, J1 comes out at time equal to 6. One of the assumptions is that the machine can process only one job at a time. So, the machine becomes available at time equal to 6 and then J2 goes and comes out at 6 plus 10 equal to 16 time units, J2 comes out. Now, at time equal to 16 the machine is free, so J3 enters. So, 16 plus 8, 24 is the time J3 comes out. So, at time equal to 24 the machine is again free, J4 enters, takes another 6 units of time, comes out at time equal to 30. So, if we consider the sequence 1, 2, 3, 4 which is the order in which the jobs are going inside. Now, the jobs come out at time 6, 16, 24 and 30. Now, as I said, there are 2 important assumptions. One is the machine is not idle at all and a machine can process only one job at a time. So, we also make an assumption that the machine is not idle or the machine is not kept idle when there are jobs waiting in front of it. Now, if we look at make span as the objective, make span is the time at which the last of the jobs is completed. So, make span for this sequence is 30. For a given sequence J1, J2, J3, J4, the sum of completion times is 6 plus 16 plus 24 plus 30, which is 22 plus 4, 26, 46 plus 30, 76. So, sum of completion times equal to 76 and mean completion time equal to 76 divided by 4 which is 19 is the mean completion time. So, given a sequence J1, J2, J3, J4, we can now calculate the make span, we can calculate the mean completion time. Let us assume that the due dates for these 4 jobs are 10, 15, 22 and 30. So, if we follow the sequence J1, J2, J3 and J4, the completion times are 6, 16, 24 and 30. I am sorry, we will assume that the due dates are 10, 15, 22 and 20 for these 4 jobs. So, the completion times are 6, 16, 24 and 30. Now, job 1 comes out at time equal to 6, its due date or time at which its due is 10, therefore, it is early. Job 2 comes out at time equal to 16, it is the due date is 15, so the tardiness is 1 here, the completion time is more than the due date, so tardiness is 1. Here the tardiness is 2 and here the tardiness is 10, so total tardiness is equal to 13 for this. So, what we have right now done is, for a given sequence we have explained how we calculate the 3 objectives. Once the completion times are calculated, all the objectives now depend on the completion time, some of them depend on the due date. So, given the processing times, you could call this as Pj, processing time of job j. We have now, given the processing time Pj of job j, we have now computed here the completion time of job j. Once the completion times and due dates are known, we can calculate the objectives. Now, the optimization problem is, what is the sequence that minimizes make span, what is the sequence that minimizes mean completion time or sum of completion times, what is the sequence that minimizes total tardiness and so on. We will now address these objectives in a little more detail. Now, as long as we do not keep the machine idle and as long as the machine can process only one job at a time, whatever order we send these jobs, the last of the completion times is going to be the sum of the processing times, which is 30. Whether we send it in the order 1, 2, 3, 4 or whether we send it in the order 2, 1, 3, 4 or any one of the 4 factorial ways by which we can send this job, the make span is going to remain the same. In fact, the assumption that the machine will not be kept idle when there is a job waiting in front of it would actually help the make span, or alternately, if we are looking at make span as the objective, then it does not make sense for us to keep the machine idle when there are jobs waiting in front of it. So, as soon as the jobs, all the jobs are available at time equal to 0, so the machine starts processing one job after another, and in whatever order we send these jobs, the total make span is going to be 30. So, make span is equal to 30. So, minimizing make span on a single machine is not a very difficult optimization problem. Any order, any one of the n factorial sequences give us the same make span, which is equal to sum of the processing times. Then we move to the total completion time or mean completion time. Now, we ask ourselves the question, if we send the jobs in the order 1, 2, 3, 4, the sum of completion times is 76 and the mean completion time is 19. What is the order in which we have to send these jobs such that sum of completion times is minimized? Mean completion time is sum of completion times divided by the number of jobs. So, whether we minimize sigma Ct or whether we minimize mct, it means the same, because you are dividing by n, and in this example we are dividing by 4. So, what we want to do is, if we want to minimize this 76, Now let us go and find out how we got this 76. 76 was got by the sum of 6 plus 16 plus 24 plus 30. Now how did we get this 6, 16, 24 and 30? Now the moment we choose an order 1, 2, 3, 4, 6 is the processing time of the first job, 16 became processing sum of the processing times of these two, 24 becomes sum of the processing time of these 3 and 30 becomes sum of the processing times of these 4. So essentially we want to have the order or sequence such that sum of these numbers are minimized. Now when we want to minimize the sum of these 4 numbers, it only makes sense to minimize all the individual numbers, because the first job that we pick, which has processing time 6, finds its place in here, here, here and here. So whatever job we fix as the first job, its processing time is going to contribute to all the 4 completion times. Whatever we pick as a second job, in this example 10, now its contribution is going to be from here, here and here. Whatever we pick as the third job, its contribution will be from here and here. Whatever is the fourth job will contribute here. So if we want to minimize the sum of completion times, we wish to minimize all these 4 of them, and whatever we are going to choose here is going to contribute 4 times, whatever we are going to fix here is going to contribute 3 times and so on. Therefore it is only correct that we choose the smallest of them first, which contributes in all the 4 completion times. The next smallest comes second, which contributes in 3 of the completion times and so on. Therefore we arrange the jobs in increasing order of processing times, and in general non decreasing order of processing time. And this is called shortest processing time. Also called as SPT. So arrange the jobs in the increasing or non decreasing order of processing times to get the sequence. Now the processing times are 6, 10, 8 and 6. So we arrange them in the order J1, J4, J3 and J2. Now the moment we order them in J1, J4, J3 and J2, the completion times are J1 has a processing time of 6, so this is complete at time equal to 6. At time equal to 6 the machine takes up J4, takes another 6 units of time, so finishes at 12. At 12 it takes up J3, takes another 8 units of time, finishes at 20, and at 20 it takes up the last job, which is J2, which has a processing time of 10, and this will finish at time equal to 30. Now sum of completion times is 6 plus 12 18, 18 plus 20 is 38, 38 plus 30 68, and mean completion time is 17 in this example. The optimum value of mean completion time is 17. So the shortest processing time rule minimizes sigma CT or MCT, mean completion time. This is an extremely important result which finds its way into other sequencing and scheduling problems. More importantly, this has introduced us to the rule which is called shortest processing time rule, where we try and arrange the job to form a sequence such that the processing times are in increasing order or non decreasing order, as in this example. Now we look at the third objective, which is minimize sigma Tj. We have already defined Tj. Tj is defined as the tardiness associated with the completion times and due dates. So tardiness Tj of job j. So Tj is maximum over 0, Cj minus Dj. Now Cj is the completion time or time at which job j is completed, Dj is the due date associated with job j. Now if the job completes later than the due date, then it is tardy. In such a case, Cj minus Dj will be positive. So maximum of 0, Cj minus Dj will be positive and tardiness will be positive. If on the other hand the job completes ahead of the due date, then Cj minus Dj will be negative, because Cj, the completion time, will be smaller than the due date. So when the job is early, which means Cj is smaller than Dj, then Cj minus Dj becomes negative and the tardiness associated with job j becomes 0. So tardiness of job j is maximum of 0, Cj minus Dj, and total tardiness is given here. Now the tardiness has two terms, which is the completion time term as well as the due date term. Since we want to minimize the total tardiness, we would like to begin with, we would like to arrange or sequence the jobs in non decreasing or increasing due dates and hope that such a sequence will turn out to be optimum. So let us first evaluate that. So the rule here that we try to use is called EDD, which is called earliest due date. Where jobs are arranged in the order of increasing or non decreasing value of the due date. Now let us apply the earliest due date rule to the example problem and first compute the total tardiness. So now based on earliest due date rule, we first sort the jobs according to the due dates. So the due dates given are 10, 15, 22 and 20. So job 1 comes first, job 2 comes second, job 4 comes third and job 3 comes fourth. So based on the earliest due date rule, the order will be J1 first, J2 second, J4 third and J3 will be the fourth. Now the moment we find out this order, the completion times are J1 starts at time equal to 0 and finishes at time equal to 6, J2 starts at time equal to 6, finishes at time equal to 16, J4 starts at 16 and finishes at 22 and J3 finishes at 30. The last of the jobs always finishes at the make span. Now due dates that we have here, so the due dates are for job 1, the due date is for job 1 the due date is 10. So due date is 10, 15, 20 and 22. Now let us find out the tardiness associated with job j. Now here the completion time is 6, the due date is 10, therefore it is early. Due date is 15, completion time is 16, so tardiness is 1. Due date is 20, completion time is 22, so tardiness is 2, and due date is 22, completion time is 30, so tardiness is 8. So sigma Tj for this example is 11. So total tardiness is 11. So, it is very customary to use the earliest due date rule to try and minimize the total tardiness. For example, if we had used, we showed some calculation here. So, when we used the rule J1, J2, J3 and J4, we found that the total tardiness was 13. The earliest due date rule gives us a total tardiness equal to 11. The only difficulty here is that while here we can say confidently that the shortest processing time will always give the minimum value of sigma Ct or mCt, we cannot say that EDD rule is optimal to minimize the total tardiness. So, EDD is not optimum always. Now, there are examples through which we can show that the EDD rule is not always optimum. Though in our example we have calculated a total tardiness of 11, which actually turns out to be optimum for this particular illustration, but EDD need not give us the optimum solution always. Then we get into the next question of, can we get to the optimum solution always, and if so, how do we get to the optimum solution always? Because the two earlier objectives of make span and total completion time, we have said that for the make span any sequence is optimal. So, I could possibly write here and say any sequence or every one of the sequences is optimal, which will give us a make span of 30. As far as minimizing sum of completion times, we could say that shortest processing time rule minimizes sum of completion time. Earliest due date rule tries to minimize the total tardiness, but it need not give us the optimum solution always. Now, in this case, if we need a method to find out the optimum solution always, then that method would either explicitly or implicitly, it has to evaluate all the 4 factorial or in general n factorial sequences that are possible, and then only it can give us an optimum solution. Sometimes it evaluates explicitly, sometimes it evaluates implicitly, because n factorial becomes very large when n becomes large. For example, if we look at n equal to 20, the number of computations is extremely large when we want to enumerate n factorial. So, we would look at methods that would implicitly evaluate a part of the n factorial, but tell us that it has evaluated that, and then by evaluating fewer than n factorial, it could give us the optimum solution. So, several branch and bound algorithms try to do that by implicitly evaluating some of the solutions, but n factorial is very large, and these sequencing and scheduling problems become hard problems, particularly when the problem size increases, when so far we have not found an algorithm that runs in other than n factorial explicitly or implicitly, because the computational effort to find out n factorial becomes exponential and very large as n increases. Therefore, in these class of problems, it is customary to look at thumb rules or what are called dispatching rules. What are called dispatching rules to try and get the best solution. Earliest due date is one such popular dispatching rule, though earliest due date does not guarantee the optimum solution in the case of single machine tardiness minimization. Now, we have seen 3 objectives with respect to single machine problems, and at the end of it 2 very important rules have come out. One is called the Spt rule, the shortest processing time rule. The other is called EDD rule, the earliest due date rule. Now, these 2 rules are also going to be used in later scheduling problems such as job shop scheduling. While the Spt provides an optimum solution to the problem of minimizing sum of completion times. Earliest due date is an extremely popular rule to address problems that have due date related objectives or due date related measures. EDD does not guarantee the optimum solution. Now there are a couple of other things which we would look at. For example, instead of minimizing total tardiness, if we try to minimize total lateness, where lateness is simply Lj is Cj minus Dj. If we want to do that, then we could realize that if we want to minimize sigma Cj minus Dj, Dj's are known, so it is enough to minimize sigma Cj, and we already know that Spt minimizes sigma Cj. So Spt also minimizes mean lateness or total lateness. And there are other rules which would say that if Spt or EDD gives only one tardy job, then it minimizes the number of tardy jobs, and so on. So there are some interesting rules and algorithms which are available, but then we have seen a small subset of it, and at the end of it I would say here that at the end of our discussion on single machine problems, we realize the two important rules have come out. One is called the Spt rule, the other is called the EDD rule or the earliest due date rule. Now we spend a few minutes on minimizing in parallel processors. On parallel processors. Now if we assume that there are two machines instead of one and they are identical, now if we want to minimize the make span, we have 4 jobs with 6, 10, 8 and 6. So with 6, 10, 8 and 6. Here again one can show that the problem of minimizing make span becomes hard and difficult. A simple rule that is often used is LPT, which means arrange them in the non-decreasing order of non-increasing order or decreasing order of processing times to get 10, 8, 6 and 6, and start allocating them to the two machines this way. So 10 goes here, 8 comes here, the next 6 will come here and this 6 will come here. If there is a fifth job, it will go here, the 6th, 7th, 8th and so on. Now here the make span is equal to 16, here the make span is 14. So the actual time at which all the jobs are over is the maximum of these two, which happens to be 16. So one could say that if we apply this rule, then the make span that we get is 16. So there are other rules and algorithms to try and minimize other objectives such as mean completion time, tardiness and so on. But as I have mentioned, at the end of discussion on single machine problems, we learned two important rules. One is called the shortest processing time rule and the other is called the earliest due date rule. So now we get into the next set of problems in sequencing and scheduling, which is called flow shop sequencing. We explain it through a small example. As we have already mentioned, a flow shop is a shop where, say we have n jobs, J1 up to Jn, and then we have m machines which we would call as M1, M2 and MM. an important condition in a flow shop is that all the jobs will have to visit all the machines in the same sequence. So, J1 requires processing on M1, M2, M3 up to MM. It also requires processing in the same order, except that the processing times are different. The same with J2, same with J3 and so on. So, it is customary to say that the machines are already arranged in the order in which all the jobs visit them. So, we could say we could call the machine which all the jobs visit first as M1, a machine which all the jobs visit second as M2 and so on. So, the machines are already arranged in the order of visit of the jobs. So, this is a typical flow shop problem, and then we would try to look at what we do for objectives such as make span, mean completion time and so on. In this lecture series we will concentrate only on the make span for flow shop sequencing. Now, we explain it through a small example. We first address what is called the 2 machine flow shop problem, where there are n jobs and there are only 2 machines. So, we take a small example to explain the n job 2 machine problem. Now, this is an example where there are 5 jobs which we call J1, J2, J3, J4 and J5, and there are 2 machines M1 and M2. Now, we want to find out the order or sequence which minimizes the make span. So, there are 5 jobs. So, there are maximum of 5 factorial sequences in which we can arrange these 5 jobs. Now, we will check about this 5 factorial after a while, but then we right now assume that there are 5 jobs and they can be arranged in 5 factorial ways, and we right now assume that one of the 5 factorial ways by which we can send the jobs is going to be optimal for the make span. So, first let us try and compute the make span for a given sequence, and then we try and optimize the sequence. So, to make it very easy, we try and compute the make span for the sequence J1, J2, J3, J4 and J5. Now, first for a given sequence, let us find out the completion times. Now, these are completion times on machines M1 and M2. So, we first send job J1. So, job J1 goes first. So, both the machines are free and they are available at time equal to 0. So, J1 requires 10 units of time on M1. So, it starts at 0 and comes out at time equal to 10. Remember that these are completion times. So, it starts at 0 and comes out at time equal to 10. So, at time equal to 10 it goes to M2. M2 is free. At M2 it requires another 6 units. So, it comes out at time equal to 16. Now, at 10 M1 is free and therefore, the next job goes to M1. So, right now we are evaluating it for a sequence J2. So, J2 comes in next. Machine M1 is available at time equal to 10. Therefore, J2 starts at time equal to 10 and finishes at time equal to 16. Now, in this case exactly at time equal to 16, J2 finishes at M1. Now, M2 is also free at time equal to 16. So, J2 straight away takes M2 at time equal to 16, requires another 12 units of time. So, at time equal to 28, J2 finishes at M2 and J2 goes out of the system. Now, once again at time equal to 16, M1 is free. So, M1 can take its next job, which happens to be J3. because we are evaluating a sequence 1 2 3 4 5. So, it starts at 16 and finishes at time equal to 24. 16, it requires a further 8. So, 16 plus 8 24, it comes out. Now, at time t equal to 24, J3 comes out of M1 and J3 wants to use M2, but M2 is free only at time equal to 28. So, J3 has to wait for 4 units of time before it could go to M2. So, right now we assume that there is enough space and buffer between M1 and M2, so that the person who is working can take J3 out of M1, keep it in the buffer space and then take up the next job. So, the next job can enter at time equal to 24 into M1. But to finish this computation, now we say that J3 can take M2 only at time equal to 28. So, at 28 it takes on, it goes to M2. So, 28 plus 9 is 37. Now, J4 can enter at 24, because at 24 it is over, the person has taken the job and kept it outside, M1 is free. So, J4 starts at time equal to 24, takes a further 8 here, finishes at time equal to 32. Now, J4 again has to wait for 5 more units, so that M2 becomes free at 37, and then it goes to M2 at 37, takes 10 more units, finishes at 47, and then it comes out. Now, at 32 J5 can enter M1. So, J5 enters M1 at time equal to 32. Once again we assume that there is enough space in between for the person to take it and keep it, so that M1 can be released for its next job. So, it starts at 32 and finishes at 44. 32 plus 12 is 44, and then it has to wait for 3 more time units to get into M2, starts at 47, finishes at 47 plus 5, 52, and at time equal to 52 all the jobs are over, and therefore, for this given sequence the make span is 52. Now, the question is, what is the sequence or what is the order in which we can send this such that the make span is minimized. We also realize something interesting from this particular table. If we see very carefully, 44, which is the time at which M1 completes all the jobs, is actually the sum of the processing times here, 10, 16, 24, 32 plus 12, 44. So, M1 is not idle till it finishes everything. Then M1 becomes idle in this case for 8 more time units or 8 more minutes. Other thing that we observe is M2 cannot start at time equal to 0 because of the flow shop condition. So, M2 can now start here at 10, and then we also realize that there were some delays that happened here. So, there was a delay of 4 units here, there is a delay of 5 units here, there is a delay of 3 units here. So, 4 plus 5 9 plus 3 12. Now, we look at this 18 27 37 plus 5 42 plus the other 10 was 52. 18 plus 9 27 37 42 10 52, but then it started at 10, 10 plus 42 is 52, M2 also was not idle. Now, sequencing and scheduling problems become important because this number at which it completes the make span largely depends on a couple of things. It depends on 2 very important things here, which is called job waiting for the machine and machine waiting for the job. Now, in this case we had situations where the job was waiting for the machine. This job was over at time equal to 24, but then the job had to wait till 28. Here the job was over at 32, it had to wait till 37. Now, you look at this case, machine is waiting for a job. The machine was available at 0, but then the machine has to wait for this job, it has to wait for 10 minutes. So, it is usually the delays that happen when the job has to wait for the machine and the machine has to wait for the job that creates this kind of an issue where the objective changes. So, the problem that we are looking at is, given a sequence we can find out the make span, what is the sequence that minimizes the make span. Now, a very popular algorithm is called the Johnson's algorithm, was developed by Johnson in the year 1954, which tries to minimize the make span on two machines. Now, Johnson not only gave a very simple algorithm, but he actually gave a very elegant proof for the algorithm. So, we will see the algorithm alone in this lecture series, we will not see the proof, but then we see how intuitive Johnson's algorithm is when it comes to solving a two machine flow sharp sequencing problem. So, Johnson's algorithm works like this. A very simple way to do it is, there are 5 jobs. So, create a small table with 5 positions. Now, find out the smallest number in this table. The smallest number is 5, and 5 happens to be for job 5 on machine M2. So, we look at this, and the rule says, if the smallest number is on M1, then come from the left, and if the smallest number is on M2, come from the right. So, smallest number, which is 5, is on M2. So, we come from the right in this table, and since that happens for J5, now we come from the right and write J5 here as the last job. So, once again look at the smallest number is 5, and check whether it is on M1 or whether it is on M2 and for which job it is. So, in this case the smallest number is on M2 and it is for J5. Since it is on M2, come from the right and write that job in the first available position from the right. So, first available position from the right is here, so J5 goes here. Now, remove this job from the list. Now, look at the rest of the table and try to find out the smallest number. The next smallest number is 6, and it happens to be on M2 for J1 and also happens to be on M1 for J2. So, when we have a situation like this, where the smallest number is coming on M2 as well as on M1, we may be tempted to believe right now that there is a tie, because 6 is appearing in 2 places, and one case it is on M2, other case it is on M1. The fact that it is on M2 in one case and on M1 in the other indicates that it is actually not a tie, and we can actually break it arbitrarily, there is no problem at all if it happens to be on M2 as well as on M1 for 2 different jobs. So, we could take either this or we could take this. Now, let us take J2 on M1 as the smallest number. So, J2 on M1 means, since it is on M1, the rule says come from the left and take the first available position from the left. So, it is on J2 on M1, because it is M1, come from the left, take the first available position. So, from the left take the first available position and put J2. Now, remove J2 from the table temporarily. Now, once again find the smallest number. The smallest number has to be is 6, it is on M2 and it is for J1. Since it is on M2, come from the right and take the first available position. So, from the right you take the first available position and put J1 here. Now, at this point we realize what we said earlier. Now, we had the minimum coming here for J1 on M2 and the minimum coming here, which is J2 on M1. We first took this and we put J2 here, and then we ended up writing J1 here. If we had taken it the other way, we would have taken this first, then we would have written J1 here and then J2 would have come here. The sequence has not changed, because the smallest number happened to be on M1 for a particular job and on M2 for some other job. So, now remove J1 also. So, 3 jobs have been put in the table, 3 jobs have gone out. So, what we have remaining are J3 and J4. Now, find the smallest number which happens to be 8, which is on M1, which is for J3 as well as it is for J4. Now here there is a tie, whether we take this J3 on M1 or whether we take J4 on M1. So as long as the smallest number happens to be on two different machines, there are only two machines, happen to be on two different machines, there is no tie, the sequence does not change or the sequence is not affected. But if there is a tie like this, when the smallest number happens to be on M1, now we could either take J3 or take J4. So first let us take J3. So since it is on M1, come from the left and take the first available position. So we take J3 here. Now remove this J3, there is only one job remaining and there is only one position vacant, so put J4 here. Now we had a tie between J3 and J4, both of them had the smallest number and it was on M1. We resolved the tie by taking J3 first. Now what would have happened if we had taken J4 first? If we had taken J4 first, we would have got the sequence J2, J4, J3, J1 and J5. So Johnson's algorithm in this, for this particular example, gives two sequences. Now two sequences happened because of a tie occurring here, and we had one sequence which we resolved by putting J3 first and then J4, and the other sequence by putting J4 first and then J3. Now let us try and evaluate the make span for both the sequences. We will first do that for this sequence. So the sequence that we are taking is J2, J3, J4, J1 and J5, and completion times on M1 and M2. So J2 goes first, J2 starts at 0, finishes at 6. Now J2 goes to M2 at 6, takes another 12 units, so finishes at 18. J3 goes next, J3 can start on M1 at 6, needs another 8 units of time, finishes at 14, but M2 is available only at 18, so it takes another 9, 18 plus 9, 27. Now J4 can start at 14 on M1, takes another 8 units, so 14 plus 8, 22. Now it has to wait till 27 for M2 to be free, takes M2 at 27, takes another 10 units of time, finishes at 37. Now J1 can start at 22, takes another 10 units of time, finishes at 32, 22 plus 10, has to wait for another 5 units for 37, so takes M2 at 37 plus 6, 43, it comes out. J5 is the last job, it can start at time equal to 32, takes another 12 units of time, so finishes at time equal to 44, and now J5 comes out at time equal to 44, M2 is already free at 43, but J5 can take M2 only at time equal to 44, takes another 5 units, finishes at 49, and now all jobs are over at time equal to 49, which is the optimum make span according to Johnson's algorithm. Now here we can see both, we can see a situation where this job is coming out at 14, but the machine is available at 18. So here is a case where the job is waiting for the machine to be free. Here the job comes out at 44, but the machine is already free at 43, but the machine has to wait for the job to come. So there is a machine waiting time of 1, which again increases the make span. So the make span increases due to two things. One is job waiting for the machine, the other is machine waiting for the job. It is only these two delays that make sequencing and scheduling problems important and scheduling and sequencing problems difficult. So based on the Johnson's algorithm, where we got this sequence, we got the make span to be 49, but we also got another sequence here. So, we will quickly try and compute the make span for the other sequence. So, here we are again computing cycle times, we have M1 completion times, we have M1, M2, the sequence is J2, J4, J3, J1 and J5. Now, for J2 it is the same, so it is 6 and 18. Next we have J4, so J4 comes here, so J4 takes M1 at 6, finishes at 14, has to wait for 4 units of time, so goes to M2 at 18 and finishes at 28. Now, J3 can start at 14, takes another 8 units of time, so 14 plus 8, 22, waits for 6 more units, goes to M2 at 28 and then plus another 9, finishes at 37. Now, J1 can go to M1 at 22, takes 10 units of time, finishes at 32, waits for 5 more units of time to go to M2 at 37, takes another 6 units and comes out at 43. Now, J5 goes to M1 at time equal to 32, takes 12 more units, finishes at 44. Now, M2 is waiting, so it goes to M2 at 44, takes another 5 units of time and finishes at 49. So, this sequence also gives us the make span of 49. So, Johnson's sequences, because of ties, if we have more than one sequence, all the sequences are optimal and all of them give the same amount of make span. Now, Johnson's algorithm gives the optimum make span for a general n job, but 2 machine flow shop. And Johnson's algorithm is based on a very simple rule that if you have n jobs, create a table with n slots, find out the smallest number in the table. Now, if the smallest number is on M1, then come from the left and put the corresponding job in the first available position. If the smallest number happens to be on M2, then come from the right and put the corresponding job in the first available position. Once a job is entered into the table, temporarily eliminate or remove the job and once again find the smallest number. Repeat this till all jobs go into this. If there is a tie, ties can be broken arbitrarily, but ties can result in more than one sequence. A tie will happen if the smallest number is on a particular machine, say M1, and more than one job has that. Similarly, tie will happen when it is on M2 and more than one job has it. But if the same smallest time happens to be on M1 and M2 for 2 different jobs, then it is not a tie. So, get as many solutions as there are ties, all of them are optimum with the same value of make span. Now, Johnson's algorithm is seen as the starting point of research in sequencing and scheduling, because for what appears to be a complicated problem with a worst case possibility of n factorial, Johnson came up with a very elegant algorithm which could solve the 2 machine case. Now, Johnson's algorithm triggered a whole lot of research in sequencing and scheduling, and for well over 50 plus years, people, hundreds and thousands of people have been working on sequencing and scheduling problems. Now, Johnson's algorithm can actually be extended to a very special case of the 3 machine problem. Now, Johnson's extension to the 3 machine we will see in the next lecture.